Ladies and gentlemen, in the last video we have seen the simplification by logic simplification by 4 variable Karnaugh maps. We saw the examples of a 4-bit binary to gray code converter and a 4-bit gray to binary code converter. So we understood how the Karnaugh map is populated with ones and zeros, and how the pairs, octets, the quads are taken, and how the terms are selected accordingly. Now in this example we see a BCD to XS-3 code converter. As you know, BCDs are patterns from 000 to 1001. These are the numbers from 0 to 9. And corresponding XS3 codes, and as you told, XS3 code is a self-complementing code and it's a weighted code. When we convert a BCD to XS3 code, these patterns from 1010 to 1111, they are not used because they are invalid BCDs, because we want to display the numbers from 0 to 9 decimals only. So the remaining things 1010 to 1111, they are invalid BCD. So these combinations do not occur at the input. Such conditions are called don't care conditions. So in this video, in this example of BCD to XS3 code converter, we will see how these don't care conditions are included in a Karnaugh map. So with that, let me start with this presentation. So this is divided into 3 sections. First is your learning outcomes, then the design of the BCD to XS3 code converter, then summary of what you learned. So in this session you will design a BCD to XS3 code converter. Then you will learn to include don't care conditions in the KMAP. Now this is a truth table of a 4-bit BCD to gray code converter, not binary but BCD to gray code converter. These are the patterns from these patterns are 000 to 001. These are the BCD patterns, and from here corresponding to 0000 we have the pattern 0011, and corresponding to 0001 we have 0100. That way every 3 is added here, and when it comes to 1001, the pattern the output is 1100. After 1001, that is 1010 to 111, all patterns are don't care conditions. So here I put a D everywhere. These are all don't care conditions. So now I have to design this x3, x2, x1, x0 with the help of 4 Karnaugh maps. So this is how I go for x3. x3 is nothing but 5 zeros followed by ones and don't cares. That is 0 0 0 0 0 0 0 0 0, then 1 1 1 1 1, okay, 1 1. Then these are all don't cares. Now these don't care conditions do not occur at the input, so they can also be grouped along with the one. So when I look into this KMAPs, you can see that there is an octet here, a group of 8 ones, or ones and don't cares. I treat these don't cares as a 1, almost similar to a 1, and there is an octet formed here, and there are 2 quads. Okay, so correspondingly I have corresponding to this octet, what does not change here is this octet actually falls into 4 rows. So everything that is B1 and B0 changes everywhere in these 4 rows, and we can conclude that B1 and B0 are not included in this. The function does not depend on B1 and B0. Then there is a what does not change in B2, B3 and B2, that is B3 does not change. So the term corresponding to this octet is B3, or next one is here I have what does not change is B0, and here it is B2. So it's a B2 B1. Then corresponding to this orange loop I have a B1 and B2. Okay, B1 and B2, B2 B0 and B1 B2. So this is B3 or B2 and B1 or B0. Now x3 is computed. Now this is a KMAP for x2. If you come here, x2 is the 0 1 1 1 0 0 0, that way. That is included in this KMAP. Here you can see that there are two quads and a pair, two quads and a pair. So that results in such a function, that is b2 bar b0 or b2 bar b1 or b1 bar b0 b2. So it becomes, if I take out this b2 complement, it becomes b1 or b0 or b2, and this b1 and b1 bar b0 bar is nothing but b1 or b0 all complement. Now you can see that this of the form some b2 bar x or x b2 x bar b2. So this is nothing but b2 exclusive or b1 or b0. So that function is also created. Now there are two parts in this that results in figure 1c. If you look into figure 1c, that is corresponding to this 101010 pattern, I can put here 10101010. Then I have this pattern. So I have two quads in this, one corresponding to this red oval and one corresponding to the blue oval. So that correspondingly I have what I get here is here I get b1 and b0 or b1 bar b0 bar, which is nothing but b1 x nor b0, b1 x nor b0. So by mere observation I can say that this b0 and x0 are complements, b0 and x0 are complements. Okay, by observation I can say that they are complements. So b0 is x0 complement. So when I summarize these equations, x3 is b3 or b2 and b1 or b0, and x2 is b2 exclusive or b1 or b0, x1 is b1 x nor b0, and x0 is b0 complement. Now the circuit is realized in this figure. You can see that this is how this circuit looks like. The BCD to XS-3 code converter looks like this, and I can run a simulation on this. I will run with the QX. I go here, I open a terminal, I open a terminal here, I type QX and QX launches. I open this BCD to XS3.sh. I have this function. Now these are my b3, b2, b1 and b0. These are my x3, x2, x1, x0. This b0, b3, b1, b2, etc. they are all connected to signals. So each one, b0 has a variation 1 nanosecond, low for 1 nanosecond and high for 1 nanosecond. And this has a variation of 2 nanosecond, 2 nanosecond, like low for 2 nanosecond, low high for 2 nanosecond. Then this is low for 4 nanosecond and high for 4 nanosecond. This is just double of that, that is 8 nanosecond. It is low for 8 nanosecond and high for 8 nanoseconds. And I run the simulation for some 20 nanoseconds or so. I drop in a digital simulation and with a Verilog model, and let me run this simulation. Now you can see that I get a truth table. So you can see that this is in agreement with my requirement. This is b0, that is 0 0 0 0 0 0 1 1 0 1 0 etc. up to 1 0 0 1, it is 1 1 0, and up to this these codes are there. These patterns actually, when I give these signals that way, the patterns actually appear. So some result is available, but in the actual practice, BCD, this being a BCD thing, only BCDs do appear at the input. So this is how the simulation works. And what you learned, you designed the BCD to XS3 port converter using K-maps and tested that. Then you learn to include don't care conditions in the K-maps. And that is the end of this video. I thank you all.